Okay, so today, the first part of the class, I'll be talking about, I'll be giving this presentation of a result of blow up in the Euler equations in the first part, and then Alexei will pick up after the break. So this is the program for today. So the blow up I would like to discuss is the theorem can be found in the paper by Elguindi from last year. So this is Elguindi 2021. Let me write here. Elguindi, Elguindi, I guess it's like this. 2021. So very recent paper. And the statement of the theorem is as follows. So let me write it and then we can discuss the ideas behind it. So the main theorem, there exists so this is a blow-up result for Euler solutions belonging to C1 alpha regularity class, right? So I'll just state the mathematically rigorous way of stating a theorem, then we can discuss the ideas. So there exists alpha bigger than 0. There also exists a function u belonging to C1 alpha to this holder space, C1 alpha of space and time. This is the time interval times R3, so we are in the full space. All right. This U is a solution of incompressible Euler equations. Like this U sol of Euler, incompressible Euler. So we want to make an assumption about the initial distribution of vorticity, right? With initial vorticity omega 0 of x. And we want to say that it decays slowly at spatial infinity. So it's bounded by some c, 1 plus, and the decay, it decays like white chalk?
Yeah, it's not visible.
Oh. Okay. So the initial vorticity decays like this. Alpha. So you keep in mind that alpha is supposed to be very small, right? So this is so the initial vorticity decays slowly at spatial infinity. So this is a what?
Press.
Press more. Okay, so this is a U solution of Euler equations with initial vorticity decaying like this, such that it blow ups, right? Such that the limit as t approaches 1. T approaches L infinity norm of vorticity, it blows up. Yeah, so this is the main theorem, right? Okay, so a quick, just two remarks of our blow-up solution that I want to make. So the first one should be the solution is actually a self-similar solution. So the blow-up is self-similar. So omega is self-similar. Let me just write the expression for omega. Omega is like this. For some psi, for some psi positive, so omega is completely self-similar, and as t approaches 1, it blows up like omega blows up like to some power beta, x to some power beta at the origin. All right. Also, so this blow-up scenario, we are considering our solutions to be axisymmetric and with no swirl, right? So axisymmetric means that the solution does not depend on the angular variable, right?
1 over 1 minus t, f 1 minus t, 1.
Psi. Psi is just a positive parameter. Psi greater than 0. For some psi greater than 0. Yeah. So this is the self-similar profile, right? F. And the second remark is that like x to as the modulus of x to the power minus beta for some beta at the origin. So so this is important. The solution is axisymmetric. Omega is axisymmetric and with no swirl, without swirl. Without swirl. So without swirl just means that the angular component of velocity is 0, right? So this is a symmetry assumption. This is a symmetry assumption. This is also a symmetry assumption in some sense. So this is the blow-up scenario we are considering. Okay, now some general facts about this scenario, right? Axisymmetric with no swirl. So in this context, in this scenario, in this scenario, if U belongs to C1 1/3 plus, right? So a holder exponent is strictly larger than 1/3. Then we have global regularity for this scenario. Axisymmetric, no swirl. If U belongs to this, then we have global regularity. Then. Yeah. Then we have global regularity. All right, in this scenario, global regularity. And the last remark is that, so the fourth is about the type of blowup that we can expect, right, in this scenario. So we also have that a condition regarding the initial distribution of vorticity. So if initial vorticity omega 0 decays rapidly at infinity, rapidly at infinity, then we cannot expect a self-similar blowup. Then self-similar blowup is ruled out, right? Then self-similar blowup is ruled out. It's not possible. Is ruled out. Okay, so this is not a contradiction, right? Because decays rapidly at spatial infinity.
But compared to this is not rapid.
No, this is very slow because alpha is very small.
Rapidly means that for some big alpha or what?
No, you have to impose some strong decay infinity. Then you can rule out self-similar blowup.
So like exponential.
Maybe I didn't quite get into this, but so the self-similar blowup is conditioning on the decay of initial vorticity. So this is not a contradiction to previous results because we are in the scenario which the initial vorticity is decaying but slowly at infinity. And also we can have indeed a blowup because we are taking alpha to be very small, right? So the only global regularity result we have for axisymmetric flows with no swirl requires the holder exponent to be strictly greater than 1/3. So this is all good. So this is good with this. Okay, so I should discuss the idea, right, behind the proof a little bit. Okay, so the idea is that our blowup solution will actually be a perturbation of some other solution to some other model. So it's a perturbation argument. All right? So I will write what this other model is, but the idea is that in this other model, we have a self-similar family, a family of self-similar blowup solution for this other model. And then we try to find self-similar blowup solutions to Euler equations near those self-similar blob solutions to this other model. Yeah, so this is quite a interesting method of perturbation, your solution. So let me write what this model is. In the paper, the author calls it the fundamental model, so I will call the same here. So the fundamental model, fundamental model. Let me just call this FM. FM. So the fundamental model is something like this. And we have a linear operator. And this L, this capital omega is just vorticity written in polar coordinates, right? So no big deal here. And this L is a singular integral operator. The following expression for L. So double integral 0 pi over 2 some k. Actually, no. Just a function of theta. And this is a singular integral, right? So it should be an S. ds d theta. All right. And k, we know what it is. It's just a combination of sine and cosine. So k is given to us. So this is the fundamental model. It's just an evolution equation for vorticity. Omega is vorticity written in polar coordinates, right? And this L operator is a singular integral operator, right? Okay. So how would we come up with this model, right? So what is said in the paper is that we can actually see this as coming from the Konstantin-Laxmaida model for vortex stretching, right? So the Konstantin-Laxmaida model is something is like this, right? So CLM Konstantin-Laxmaida model for vortex stretching, but something like this, right? So you get your evolution for the function f, and take f times h of f. H is the Hilbert transform of f, right? So this is the general case of the Konstantin-Laxmaida model that they use to study vortex stretching Euler or Navier-Stokes equations. So this fundamental model has the same spirit as this model, right? So the author says that you could simply, I mean, not really simply, but you take this model, this Konstantin-Laxmaida model, and instead of taking the Hilbert transform, you just switch, you just replace the Hilbert transform with this L operator, this integral, this singular integral, right? And what makes So in general, if you replace the Hilbert transform with some other operator, it's not clear that the model is solvable, right? So in order for the model to be solvable, all the symmetry assumptions play a big role, right? So this is what makes this so-called fundamental model be solvable. Instead of it allows you to replace the Hilbert transform with just this integral, this singular integral operator, right? So you should replace. The spirit is you replace H by L. Okay. So why is this model so important, right? So the main property of this model, so the fundamental property of this model, is that it possesses a family of self-similar blow-up solutions, right? So Fm, the fundamental model, Fm. So this is a big property. Fm has a family of self-similar solutions, blow-up solutions. Has a family of S, right? Self-similar blow-up solutions. So this is why this is important, and they take the following form: these self-similar solutions. Omega of R theta T. This is for some gamma. So this is all polar coordinates. Theta, the angular variable, R, the radial variable. 1 over T, and also the self-similar profile R 1 over T blow-up solutions. So like this. For actually any gamma you plug into here, right? Okay. Okay, so the idea is that we have these blow-up solutions, and then we want to search for Euler solutions near those blow-up solutions, near this, right? And then actually, there's an important fact. So this self-similar family is stable, right? So this is important. Self-similar solutions, so stable. In the sense of, in the sense that there is an open set, this family forms an open set of solutions in the topology of C1 alpha space, right? Right?
The solutions which blow up asymptotically like this, they form an open set.
This forms an open set, yes. This for this fundamental model, right?
Don't we need any kind of information on the kernel K for us to determine this? Can we just choose the kernel K to be the Hilbert transform?
No. Yeah, so, okay, K is given to us. K has to be chosen like this. K of theta is sine theta cosine theta. to the power square. And there's a 3 here, and this is square. So this kernel is actually important for this to be solvable in order to find the solutions, right? Yeah, so the kernel is chosen beforehand. Yeah, so this is the fundamental model. It has a stable, self-similar family of blob solutions like this for virtually any given gamma function you plug in here. And the idea is now to search for Euler solutions near those solutions, right? So we make the ansatz. So let me write the Euler equations in the evolution for vorticity in these polar coordinates, just so we can see it. So this should be Euler as a perturbation of the fundamental model. Euler as perturbation of Fm. Right. Yeah, so this is quite remarkable, right? So we can write Euler equations as a perturbation of this model. So this is very something, right? So the evolution equation for vorticity in polar coordinates arising from Euler equations, let me just write, is the following. And there are some functions that I won't write explicitly. A, B, alpha R, dr omega. Yeah. Then this should be equal to other function of omega. So this ABC here just a combination, just function of this stream functions, right? So we have also an equation for the stream function, but I won't write it in here. And then we try to look for solutions near these solutions. So we make the ansatz, right? To take omega like a perturbation of this. So we take omega So we perturb by using this parameter mu of t. F 1 minus 1 plus mu of t to the power 1 plus lambda, right? Yeah, this should be an R. Yeah, an R. Yeah, there's also a function of theta. Right. So we try to make this work, essentially, right? So we try to find a F such that this, so we plug this type of ansatz in this equation, and then we will get an equation for F, right? That F must solve in order for omega to solve vorticity equation from Euler.
The second line is Euler.
The first line is Euler.
With some ABC
Is functions of the stream functions given also by Euler.
okay. It's some operators of
Yeah.
omega. No?
Mm-hmm.
And then this is answer. Okay.
Yeah, this is answers. And then what we do is that we also make the following assumption on F. We take F to be something like, so alpha over some C, gamma of theta, 2z, z, 1 plus z, square, plus a perturbation, G. Okay? So this is ansatz, this is Euler, and this is F written as a first order term in alpha, right? And G will be shown to be of order alpha squared. Okay? So this is a perturbation. Okay? So what we do is that we plug these ansatz in Euler. We get an equation for F, which is the same of getting an equation for G, right? So we have to, so the following equation for G, so this is the following equation for G that we must solve in order for F, solve the equation for F, and omega solve Euler equation finally, right? So G must solve G must solve this equation, some other operator L, LT of G, P, and some nonlinear terms. So G must solve this equation. So what we have is the following. So if we find a solution, a G solution of this equation is the same as finding a solution, an F that satisfies a certain equation, which implies that omega will satisfy Euler equations, right? So this would imply that this is actually a solution of Euler equations, right? And the solution will be a perturbation of that. So all we need to do is find a solution for this equation. So we need to find a G that solves this equation. And then we are done, essentially. So this is just the final step. So the solution will be, G will be of order alpha square. All right, so what we do is just a little trick. We transform this equation into an evolution equation by introducing a fake time variable. So we make this into a transport equation. So I will write this, nevertheless, in a fake time variable. So in a tau variable, the tau writes this fake time of, let's say, h plus whatever we have there. So what we have there is L of t of h equals p n 0 n plus n star. So all these n's are nonlinear operators, and p is a projection operator. It's a projector into the divergence-free subspace of the Sobolev space we are working with. And now this Sobolev space where these estimates are done, they all are embedded into C1 alpha. So this is okay. No problem there. Okay, so this is so we transformed this into an evolution equation by introducing this fake time. And it turns out that this equation, this last equation I wrote here, is actually Euler up to linear terms. So this means that this kind of control the higher order dynamics of Euler equations, right? So this is something also that these models, this fundamental model implies. So this is something additional. So and what this means that all the traditional theorems about existence and uniqueness of Euler can be applied here. So like the Bill-Cotton-Maida criterion can be applied here in order to find it. A global solution for H, right, for H. And this is what indeed we can show. So we can solve this globally in the tau variable, so, right, this fake time variable. So we can solve globally. Solve globally. Solve globally in tau, right? In tau variable. In tau. So solve globally in tau. And then our G, our solution to this, will actually be the limit of H as tau approaches infinity. So if you take, so we solve globally in tau, this equation, and we take G to be the limit as tau goes to infinity. So we can make tau go to infinity because H is globally defined of H. H is a solution to this. Tau R theta. Okay, so this is so this G will turn out to solve this equation for the perturbation. So this is our perturbation. This perturbation solves this, and it's equivalent to find F, which solves another equation for F, which is equivalent to find omega like this, which solves Euler equation. So therefore, we have find vorticity, right? A self-similar vorticity, a self-similar solution of Euler for vorticity, which blows up. Self-similar.
Can you repeat? So when you take the limit of tau going to infinity, what do you gain?
You gain your solution for this equation, for the perturbation equation.
Okay. Stationary.
Yeah, it's stationary in this fake time variable. So this is just a kind of a regularization procedure, like you introduce epsilon plus Laplacian, and then you take it to 0.
Gives exact solution to Euler?
Yes.
But what then? How do you use this family of asymptotic solutions? Of family of blow-up solutions before?
Sorry?
So that you use this family on the left
Yeah.
to approximate.
Mm-hmm.
How
Yeah. Oh, okay. So we have a mu here, and a lambda here, and for this to work, mu and lambda should be small. Mu lambda small. So we are perturbing. So this omega is a perturbation of this solution to this other model. Okay. So this should be small. Mu lambda small, so omega perturbation. And then we try to make these ansatz work, right? And why it works? It works, well, it works indeed. All the dynamics are encoded into this fundamental model, this L operator, and also on this last equation I wrote here. So this equation controls the higher order dynamics of Euler equation. So everything is linked together in the end, right? By this fundamental model, the so-called fundamental model. And in the end, we get a transport equation in this fake time variable, which somehow encodes the higher order evolution dynamics for Euler system. And this can be solved globally in time, in fake time, in tau variable. And then if we wish to solve for G, this equation, right, to find our perturbation, we take the limit of this H solution here, this H, which solves this. As this fake times goes to infinity, in the end, G is just a function of R and theta, right? So we have a solution for this. We have a perturbation G. We can plug it into our profile F. And therefore, we can find the omega. So this answer actually satisfies Euler system, right? For mu, lambda, alpha, everything should be very, very small here. I think in some point of the paper, Elgindi takes alpha to be less than 10 to minus 10 for it to work. Yeah, because so to prove that this is actually true, right, that this family has a self-similar family of blow-up solutions, it's actually a huge work. It takes a huge amount of estimates. And all this parameter, in the end, I think in the end he chooses alpha to be 10 to the minus 10. So,
Almost singular from the beginning.
Sorry?
It's almost singular from the very beginning. Because if it's alpha is 0, it's already.
No.
This is already infinite.
No, we have a 1 here. A 1.
No, but I mean C1 alpha. So it's,
We have a 1.
okay, I see.
Yeah, so what this means in the end, in this blow-up theory of Euler equation is that I wrote here, if alpha is strictly greater than 1/3, we have global regularity. So it seems, I mean, it suggests this, and these results that I presented here suggest that this is actually sharp, right? 1/3 is sharp. So seems might be sharp. So alpha equal 1/3 is sharp, perhaps is sharp? Question mark. Right.
Sorry, shouldn't K be singular? I think it might be missing a piece.
No. Okay, no.
Because this operator should be a singular integral, right?
Yeah, so we have an S here.
Oh, sorry, that's nice.
Yeah. So we have an S. Yeah, so this is what I wanted to present. So I think time is good. Any more questions?
But energy is finite, right?
So this is a nice question. So what he says is actually, in this paper, initial energy is not finite. But what he argues is that in a previous paper, I think of the same year actually, you can make the initial condition to have final energy, a finite energy, if you introduce a C1 alpha forcing.
Okay, so just to kill the far away part.
Mm-hmm. So he says that this can easily be modified if you introduce C1 alpha forcing, and then the initial solution, initial condition would have a finite energy, and this all would be the same, essentially. All right. Yeah, so one last comment is just that, so what this means is that we cannot try to extend somehow this theory of regularity in C1 alpha scaling at least, right? In Holder scaling. Because there is an alpha, I know it's very small, right? But that there exists an alpha for which this Holder space theory, regularity theory cannot be, you cannot extend it to for any alpha below 1/3, right? Okay, so this is it. So I'll like a break, right? Break. Till 16. Okay.
So hello. So we continue. So let's continue about the issue of the post-blow-up dynamics. So I just recall you briefly where we stopped. So we were looking about two situations. So one situation with when we have a ideal system, for example, Euler. And this ideal system, whenever you have temporal dynamics, which starts with some initial moment 0, the situation is that there is a finite time blow-up. So there is a time Tb where when something happens with the solution, which we call blow-up. And usually what happens, like in Euler that we saw, what must happen is that viscosity should be infinite. Viscosity is derivative. Usually some derivative diverge, but actually I would say that the general property of what happens at the blow-up point is that it's the point when the Lipschitz condition is not anymore satisfied. No Lipschitz continuity. So it's a differential question, maybe in infinite dimensional space, but whenever the right-hand side is Lipschitz continuous, you can continue. If the right-hand side become not Lipschitz continuous, then we cannot continue. At least we cannot continue uniquely. And this is what we saw in Burgess. So we can continue until there is a blow-up point, or there is a unique solution, and then you can relax a little bit the definition of a solution, but at the same time you don't have uniqueness. So in a parallel with ideal system, we have a regularized system. Regularized system, which is Navier-Stokes in case of fluid dynamics. And the property of the system is it's all right. So it's expected to be all right everywhere, and it depends on a parameter which we call viscosity, nu positive, and this is exactly the same parameter which, so whenever you put it to be 0, you recover the ideal system. So you perturb the ideal system with the parameter nu, and it becomes all right. So the question is whether there is a limit. So whether we can whether we can understand somehow the solutions of the first system by considering the regularized system with a small nu, and we saw that in the case of Burgers, we have a uniqueness for after blow-up, obtained from the limit of viscosity going to 0. At the same time, Euler Navier-Stokes, presumably the limit does not exist. Okay, so certainly Euler Navier-Stokes is a very complicated problem, right? So the Euler Navier-Stokes is a very complicated problem. Even the toy model that we discussed before, like shell model, they're also very complicated problems. So there is no know any clear results of what happens. So, which means that let's consider something simpler. So let's consider something very simple. So what can be? We start by considering the most probably simple example that you could cook from this formulation. So what we want to have? We want to have a system which becomes Lipschitz, which is Lipschitz continuous until certain moment, and it's not Lipschitz continuous, and then we have non-uniqueness, and we see how the regularization may influence this non-uniqueness. How much what can happen in principle. So the simplest system, first of all, in order to make everything simple, we should move from partial differential equation to ordinary differential equation. So the simple example. So first, what we do is from partial differential equations, we go to ordinary differential equation in finite dimensional space, but then in ordinary differential equations, the simplest case is on a line. So let's consider just one ordinary differential equation on the line. So the question whether we can reproduce that scheme just on straight line. So by differential equation on the straight line. And in fact, we can. So the simplest case corresponds to the system which is that's right, dx dt equal f of x. And now what we will, so x is a real number. So we have to incorporate somehow Lipschitz discontinuity. So Lipschitz discontinuity for ODE is a property of the function f. So let's remember what is Lipschitz condition. So Lipschitz condition is that the difference between function f at two different points. So is that there is a constant such that the difference of function at two different points is smaller or equal than this constant by the difference between points for any x and y. So it's clear that if the function is differentiable with with bounded derivative, it's automatically satisfied. So it's just slightly weaker. So it doesn't have to be differentiable, but usually in practice it means that if it's differentiable, it's Lipschitz. If it's not differentiable, like Holder, it's already not satisfied. So this is what we need. So f should not be Lipschitz continuous, but now if we want to construct the simplest case, is that in that case we can consider f to be Lipschitz continuous everywhere except for a single point. So just put Lipschitz discontinuity at a single point. So singularity at a single point. And of course, it should be origin, because it doesn't matter. So singularity at the origin. So now we can really choose what is f. So we take f to be modulus of the cubic root. So modulus of the cubic root. So what this function is this is a function which is positive x. So it's like this. Like this. So it's not Lipschitz continuous at the origin. So this point is not Lipschitz continuous. Obviously, because the Lipschitz continuous, this is not satisfied for any key. Derivative is infinite. And this is, of course, academical example, but it's actually not disconnected to fluid dynamics because of the observation. So we can make interpretation to this example. The interpretation can be that x, let's make it separate. Consider two particles moving in turbulent flow. So that's x of t and x prime of t. x1 of t, x2 of t. So two particles. Not one. A, B. So then the distance between them, the difference xa minus xb. So derivative, so let's call it x. X the distance between two particles. So then whenever x is very small, so we can compute that dx dt is the difference of the speeds, right? Because so it's speeds ua minus ub. But we know that whenever the speed difference, the distance is small, in a Kolmogorov theory, which is not exact, but it's rather well approximates the flow. The Kolmogorov theory tells that the difference between the speeds in a turbulent flow is of order 1/3, is cubic root of the distance. And this is exactly what we do. So let's put like this. No. Okay. So our ODE mimics this situation. So we take x real, dx dt. So our ODE. Dx dt equal what is here? Model x 1/3. So essentially you can interpret this equation as a kind of a very rough approximation of two particles which come together and separate. So let's study this situation from point of view of the analysis. So, okay, let's remove this. So let's just solve this system. This system can be clearly solved. So we solve this system for initial condition x0 equal x of 0, and we assume that it's negative. It's negative, so what then happens is that the solution as a function of time, we will have initial condition below. Derivative is always positive, so it will increase. We will now show that it will reach 0 at finite time. It will come to 0 at finite time, which we will call blow up, because this is a point where we lose Lipschitz continuity. So this will be our blow up. The solution reached the point with which is not Lipschitz, and then we will see what next. So what? Okay, so just let's make the analysis. Okay, so we start with x negative. Whenever x is negative, so we can write equation dx dt equal x 1/3. X 1/3 is well defined for negative x, but since it's a modulus there, so it should be -3. It's like this. So I just remove modulus. And then you solve it. So it's dx over minus x 1/3 equal dt. And then, so separation of variable, then integrate it. So on the right-hand side, you get time. And on the left-hand side, you get, so this is, so it gives you minus dx to third, so it should compensate for this, so 3/2 equal dt. And then integrating you integrate between 0 time and t, so on the right-hand side it will be t, so on the left it will be minus 3/2 x to third plus 3/2 x0 to third. So I just integrated and I put the arbitrary constant of integration such that it satisfies the initial condition. Okay, so this is arbitrary constant of the integration, and we need to satisfy this condition that at time 0, this should be also 0. And so it should be x0. Okay, so we call TB equal this number. So you see x0 is negative, but here there is 2, so it's positive. Okay. And then what we write is that we put this on the left, so you have 3/2 x 2/3 equal TB minus t, and then x is 2/3 TB over t 3/2. So indeed, the solution starts at point x0, and at finite time tb, it is 0. So you see, if the function would cross 0 in a smooth way, you never enter the point, in the differential equation. But since it's non-Lipschitz, you enter 0 at finite time, and we know even what time it is. So here we directly compute the blow-up time. So what next? The next is you take x positive, and then you get the same equation, but with a plus. And essentially, so what changes is you can just change sign of t. So the solution will be okay. When I take the root, I also forgot here minus, no? Because when you put this, you should take care of the sign. Okay, so this minus here. So for another case, you doing the same analysis but with different sign. You see here there is a different sign, so you get x equal two-thirds t plus for any T star. So you get a class of solutions which at T star starts from 0 and just become positive. So in particular, we can take T star to be TB. So when T star to be TB, we just continue the solution symmetrically up. So there is a solution. So in principle, we can pass through the singularity, but there is an important exception, because it's not the only solution. There is another solution, because another solution is, so this is x of t. Another solution is just 0. It also solves the equation. So it means that what you can do from the blow-up point is you can stay at 0 identically until whatever time you choose, and then just depart with this solution. So which is exactly the same curve, but starting from that point. Which means that there is infinitely many solutions. So the infinitely many solutions after the TB. Because you can come to TB and depart immediately, or you can wait some time, depart, or you can just wait forever. So there is infinitely many solutions. So what solution you choose? In order to see that this is, before looking how we choose the solution, let's just have some flavor that it's really blow up in this case. So for example, in case of Euler, remember that we had vorticity has to go to infinity. So in our case, dx dt, which is modulus x 1/3. So the velocity goes to 0 at blow-up time. But if you compute, for example, next derivative, so the acceleration, so from the negative side, it will be minus. So it's minus, so it will be d dt dx dt. And this is d dt from minus x 1/3. And this becomes 1/3 minus 1/3 1 of x 2/3 dx dt. As again minus, so it's 1/3. And this is x 1/3. So it already goes to infinity. So acceleration goes to infinity. So you enter with 0 speed, but with infinite acceleration. See? So it's a simple example, but already gives you something. So you see that you really have a kind of blow up in some sense. Okay. So now we want to check which solution is. So if we regularize the system and whether it will choose one of the solutions of the original system. So we make a regularization. So regularization is actually a rather simple procedure, because what we need is, instead of the function which is singular at 0, we should create a function which is not. And the easiest way is just to make it smoother. So this is a regularization, and the distance at which you do, you call nu. So you can define a sequence of functions. So the function f, we define function f nu, where they coincide everywhere except for the distance at the height nu, you make it smoother. So let's see what will happen. And of course, so what we can do is that it's vice versa. So it goes to our original f as nu goes to 0. So this is our regularization, which is essentially similar to what viscosity does, because viscosity removes all strong gradients. So whenever you have strong gradients or strong high derivatives, viscosity make it smoother. So the region where we have infinite derivative, it just makes it smooth. Good. So what we have? So essentially, the simpler way is just to consider the horizontal, just to make it smooth in the horizontal way, so we can compute. And what we can do is we can compute how much time the system spent in this regularized region. Time in regularized region. Time in regularized region. So how you compute it? So you have to divide the distance that should be traveled. So this distance is, remember this is cubic root. So this distance is twice nu cube, right? So this is nu cube, since this is nu, and then this twice nu cube. So the time in the regularized region is, you have to divide the distance. So this is delta t is a distance which is 2 nu cube, divided by the speed, and speed is f, which is nu. So the time spent in the regularization region is 2 nu square, and it goes to 0 as nu goes to 0. Which means that smaller and smaller regularization parameter you get, smaller and smaller time you spend here. And whenever you pass to this side, you're already far away from 0 solution. So you immediately go with a solution which is upper. So it means that the selection, selected solution is always the one with t star equal tb. So whatever regularization you put, except for something very, very special, so any generic regularization you put, it will choose, it will select a unique solution. So this will be selected. Something in the spirit of Burger's equation. So we have a system, we have infinitely many solutions. We put regularization, and as we see now, it doesn't matter how we put regularization, as far as it stays away from 0. We always select very same solution, the one which leaves this point directly. Good. So the next step is, so this is the simplest example. And the message from this example that already on the simplest example we have a situation which is resembles very much the situation with the Burgers equation, but only that. So there are no other non-trivial possibilities. So, in order to have non-trivial possibilities, we should make our models more complicated. So the more complicated is that we still will be we'll consider still ODE, but not on a line, on some arbitrary dimension. So we will start with 2 dimensions. So the ODE on a plane, and we still will consider the singularity at just single point at the origin. Just 1 point, so one point singularity. Some more general citation. So we have x dx dt same equation. Now in dimension d. And we should create singularity at the origin. And what we will do is we just will generalize this function, which was, which one? This function. So we consider polar coordinates. So let's write polar coordinates. So r will be distance to the origin, and which is positive real number, non-negative. And y will be the unit vector in the direction of x. So y is a point on a sphere. So if it's a sphere in d-dimensional space, so it's d minus 1-dimensional sphere. So on a plane, r is a distance to the point, and y is a vector to the pointing to the unit sphere. Good. So what we do is we take function f of x to be r alpha, function of y. So we already see this self-similar ansatz in some sense incorporated, and alpha is smaller than 1, which means that it's non-differentiable at the origin. So it means that it's non-Lipschitz. At x0, when r is 0. So this already gives us a full large family of systems which all differ by this function f. So we consider so let's consider example, just simple example. So plane, and in this case, y is a unit vector, so y can be written in the polar coordinates as cosine alpha, sine alpha, sine phi. And then we take function f to be of a very specific form. So we take f to be. So this is an example from a paper. So it's sine. So f of y means that f should be y is parameterized by phi, so it's f should be function of phi. So we take phi plus p over 2. Oh, p over 4. Cosine phi sine phi. So this is y. Minus sine 2 phi over 2 minus sine cosine phi. And so this is orthogonal to phi, no? Orthogonal to y. So this part is parallel to y, and the other part is orthogonal to y. So now we can see what these fields means. These fields essentially define, up to a constant, these fields defines the vector field on a plane. So let's just take it separate. So this part gives you the part of the vector field which is radial. So it's parallel to y, so it's always directed in the radial direction. But it changes sign. So on this plane, it depends on sign of this function. As this function changes the sign through this diagonal. So what happens is that in the upper plane, it's positive, right? And on the left, lower part, it's negative. So here it's facing outwards, here it's facing inwards. So this vector field. And this vector field is circular. So it's tangent to a circle. And it changes the sign with twice the phase. So you see it's positive here. So it gives this direction here. And the same on the other side. When in this part it's like this, and this part is like this. So these are two vector fields, and now we put them together and just draw the vector field of the, when you substitute this function in this part. So what is the vector field of f, small f? So this will be a vector field of small f. So immediately you can check that the x's are solutions. In this form. The vertical axis is also. Then there is a singularity right in the middle. And then the other part of the solutions is like this. So there is, on this corner, you see it should be going, it's a sum of this and this field. So it gives you this kind of trajectories which never touch neither of the axes. In this part, the sum gives you trajectories which all enter the origin. Symmetrically here there will be same trajectories but leaving the origin. Then we remember the tangency condition. tangency may be incorrect. This. And here, you see, so they exit and enter. So that's a vector field of our system. So what you can see? So what you can see is that whatever initial condition you have with x1 negative, you always enter to the origin. And for the same reason that we had before, if alpha is smaller than 1, you enter at finite time. So whatever initial condition you have, in finite time you enter the origin. After you enter the origin, you have infinitely many possibilities. You can stay at 0 as long as you want and leave at any moment. And you can leave along any trajectory that looks upwards, because all of them leave the origin. So there's infinitely many solutions, even more than we had before. So there's not only the combination of 0 and some solution, but it's 0 solution and infinitely many solutions coming out. So there's a lot of solutions. So the question for this system, and in principle for other systems, for higher dimension maybe and different f, what will be the selection? So if there is any reason why some solution is preferable to others. And usually what we will do is already anticipating the same idea. What you can do is you make a regularization. So you draw a circle of size nu. So nu is our viscous parameter, and you say, okay, inside I change it. I make it smooth. In some way. I make it smooth. Whenever you make it smooth, everything is regularized, because the only point with singularity was at 0. So when you smooth this vector field at a small neighborhood, solutions are defined for all times. Then you can take the same initial condition and find solution for infinite time and take nu going to 0. And now the question whether it will give us unique solution or whether it will give us non-unique solution, or what we will see is that in some cases it will give random solution. So that's we're random with certain. Actually, the most interesting situation that we are going to check is that actually it may give a different solutions going out with different probabilities. So the probability comes out of nothing. But before really going to, today we will not have time. Before going to regularized system, let us take care of original system when there is nu is 0. So singular system, and then we will make a rescaling. So we do rescaling, which is remove singularity, but not removing singularity from a vector field like we did here. It removes it from a formulation. So it reformulates the system in a smooth way, in such a way that we can really understand the dynamics better. So what we do is we give some definitions. So first of all, this function of f, it is convenient to split it always on two parts. One is radial, another is angular. So we always split it into pieces. One will be radial along y, another will be spherical. So what is here? So fr is real is a real perfector multiplied by the vector, and this is Fs is spherical. So in other words, any vector for any point y, so remember y is a point on the unit sphere. So whenever you have point y, we have vector f at this point. So what we do is we split into the two pieces. One is normal Fry, another is tangent. So it's tangent, which is Fs, so it's not SD minus 1, it is on a tangent SD minus 1, on the tangent space of the surface. Tangent at point y. Okay. So radial and spherical component. And now what we do is we introduce new coordinates. So what we do is we, instead of radial distance, we take log of it. So distance is always positive except at the singularity, so we can just take a log of it and call it z. So it's a real number now, so not necessarily positive, or the distance can be written as exponent of z. So in this case, singularity, when r goes to 0, it corresponds to z going to minus infinity. So this is new coordinate, and then we consider new time. So new time will be considered because what we want to do is when we approach the singularity, you see r is getting smaller and smaller, but what logarithm does, it stretches the coordinate. Yeah, because logarithm stretches the axis near 0. And what we want to do is also to stretch time. So when we come closer to here, though in original time it comes to infinite time, but now we will see watches which go faster and faster and faster together with dynamics. So exactly what we do is we take ds equal very special thing. So it's exponent minus 1. So it will be dt divided by r1 minus alpha. So you see, when we come closer to the singularity, we divide by small number. So we stretch time. So in z, it's exponent minus 1 minus alpha z dt. Okay. So the remaining part is just direct calculation. So now let us write equations of this system in new coordinates. So we have x is ry, right? It's polar coordinates, which is exponent zy. So now dt can be written as from here, right? So it's ds dt like this. Correct? So what we can write that dx dt, which is this dx dt, is what? It is it is exponent of minus 1 minus alpha z d ds from Ry, which is Ez y, like this. So the next we open it up. So the first is exponent Ez. Ez cancels this first. So the E alpha z d z ds y. And then we differentiate y. So it will be plus E alpha z dy ds. And on the other hand, it equals to R alpha f of y, just by definition. So it was our system here. And R is exponent z. So it will be exponent alpha z. Then f has this structure. Plus the other part. And now you can see that actually they should be equal term by term, because this is radial, and this is tangential, this is tangential. So we get two equations. So one equation is the last one, dy ds equal f s of y. This is first equation. And then there will be second equation which tells you that dz ds equal fr of y. But here there is no z, so we can just integrate it. Z of s is z0 plus integration from 0 to t to s. The second. And the last is this, which gives you that dt, just sweeping it around, which means that time you can also integrate. So time is 0s. So what we have? We have actually one single dynamical system on a sphere. So this is a regular system on a sphere. So it's a regular system on a sphere, so it lives on a sphere. With this, and fs is smooth function. So its smooth function is also limited because it's on a compact surface, so it never blows up. No blow up. So this part is globally defined. And whenever you have a solution with initial condition which is given by the initial moment, you just, as an integral, you compute z, which gives you distance. It also finite at each time. And then by this formula, you compute time. So somehow we took our system, which is singular, and mapped it to a system which is regular. Right? what we did is we took our system which was in n dimension singular, and so it had some solution that could go to the infinite time or exit infinite time the singularity, and we mapped it to the system which is on just on a sphere. So it's just some trajectory on a sphere, but original time system was in time t, and new system in time s. So of course, the fact that the system in finite time goes to singularity means that, and this time is never blows up. It means that whenever s goes to infinity, time does not have to go to infinity, in fact. So this integral may, and you really have this exponent. So this integral can converge to a finite number. So we have a system which is globally well defined in new time s, but infinite s does not imply infinite t. And this duality between the regular system on a sphere and the singular system in the original space will give us, actually will explain us how the regularization works in general. So it's actually this duality which we'll discuss today. Is Thursday, no? Yeah. So we'll study tomorrow. We'll explain actually how the property of the system, which is original implicit system, will tell us which solutions will be and in which way will be chosen by regularization. So how regularization actually, we will see that regularization actually doesn't have much freedom. It's the effect of regularization, whatever you do here, is very much restricted on whatever happens on the sphere. So this is tomorrow. Thank you.